Hello students, in this video I am going to talk about quantum numbers, and towards the end of this video I have also kept some MCQs. I promise that will be very beneficial for you to gain the deeper insights regarding the topics, so please watch till the end of this video. What are quantum numbers? So let me begin from the definition first. So quantum numbers are a set of four numbers that determines energy, spatial orientation, means orientation in a space around the nucleus, right? And spin of an electron in an atom. So in simple words, it means quantum numbers give us information about the energy of an electron, okay, energy of an electron, of a particular electron. It gives a position of an electron, okay, how far is the electron from the nucleus. So it gives idea about the position of the electron from the nucleus. Yeah. Similarly, it gives us idea about how the electron is revolving around the particular nucleus. So how it is revolving, and in which direction, in x-axis or y-axis or z-axis. Okay. And lastly, what is the spin of that particular electron, spin up or spin down. So these informations are provided by the four quantum numbers. So once again, I repeat, quantum numbers are a set of four numbers that determines the energy, spatial orientation, and spin of an electron in an atom. The four quantum numbers are principal quantum number n, small n, we denote by small n; azimuthal quantum number, denoted by small l; magnetic quantum number, denoted by small m; and spin quantum number, generally denoted by small s. Principal quantum number. So basically, principal quantum number, it denotes the cell or main energy level of an electron in an atom. So in simple word, generally we represent cell by letters like K, L, M, N, O, P, right? So in terms of quantum number, we represent cell by the number 1, 2, 3, 4, 5, 6, and so on. So if n is equal to 1, principal quantum number n is equal to 1, it means we are talking about K cell or first cell. It means electron is in the first cell. If we are writing n is equal to 2, it means electron is in the second cell. N is equal to 3, it means it is in the third cell or it is in the M cell, and so on. Okay, so possible values of n will be 1, 2, 3, 4, 5, 6, and so on. By the help of principal quantum number, we can also determine the distance of a particular cell, okay, from the nucleus. So for example, for hydrogen, Niels Bohr have obtained a relation or formula that radius is equal to 0.529 into n square, where n means the principal quantum number, okay. And for first quantum number or first cell, K cell, the radius will be 0.529 into 1 square. Yeah, so the answer is 0.529 angstrom. And for second cell, that is L cell or n is equal to 2, the radius will be 0.529 into 2 square, means 4 angstrom. Similarly, for third cell or M cell or n is equal to 3, so radius will be 0.529 into 9 angstrom. Okay, but keep in mind that this formula or this relation is for only for hydrogen, okay, not for other atom, for hydrogen. Similarly, for other hydrogen-like species, okay, that means having single electron system like helium plus or lithium 2 plus or beryllium 3 plus, we can find the radius of the particular cell by using the similar equation 0.529 into n square by z. So where z means the atomic number, right? Z means atomic number. We can also find the energy of an electron of a particular cell by the help of quantum number, okay. For example, for hydrogen, Niels Bohr have obtained the relation that energy is equal to minus 2.18 into 10 to the power minus 18 by n square joule, okay, and it's for single atom. So it means if you want to measure the energy of a second cell, n is equal to 2, right? Electron is revolving here, suppose, and if you want to measure the energy of this particular electron that is revolving in second cell, n is equal to 2, then simply put here 2. So the answer will be minus 2.18 into 10 to the power minus 18 by 2 to the 4. Yeah, so joule per atom, okay, joule per atom. So this is the answer for second cell. So in this way, we can also find the energy of a particular cell or particular electron by using principal quantum number. And for hydrogen-like species like He plus or Li2 plus or B3 plus, that is species containing a single electron. Okay, so the expression for energy of different cells or energy level, that is given by minus 2.18 into 10 to the power minus 18 into Z square by N square. So where N means principal quantum number, right? So you can put here value N1, N is equal to 1 or 2 or 3 or 4, right? And Z means atomic number. What is Z? Z means atomic number. And you will get the answer in joule. And this is for one atom. And if you want to measure per mole, then you can multiply the answer by Avogadro number. You will get the answer in per mole. Okay. Now let me explain about the azimuthal quantum number. It is also known as orbital angular momentum quantum number or subsidiary quantum number. The azimuthal quantum number determines the shape of the orbital or subshell. Okay, so basically in simple words, it gives us idea about in which subshell the electron is revolving. Okay, so what is the distribution of electron around the nucleus? What is the shape of the electron cloud around the nucleus? So that information is given by azimuthal quantum number. So if the shape of electron cloud is spherical, yeah, then L is equal to 0. If the shape of electron cloud is somewhat dumbbell-like shape, yeah, then L is equal to 1. So previously we used to write S, P, D, F, yeah, G. So for that we write L is equal to 0, 1, L is equal to 2, L is equal to 3, L is equal to 4, and so on. And one more thing, value of L depends upon the value of N. Okay, so in next slide I will show you. And the value of L ranges from 0 to N minus 1. So if the principal quantum number is N is equal to 4, then azimuthal quantum number for will be 0, 1, 2, 3. So in this way, the value of azimuthal quantum number depends upon the value of principal quantum number. So if the electron is orbiting in spherical space, yeah, the distribution is spherical around the nucleus, then L is equal to 0. If it is in p orbital, yeah, then L is equal to 1. If it is in d orbital, L is equal to 2. If it is in f orbital, L is equal to 3. So these are most commonly used in terms of letter, and these are in terms of quantum number, okay, or azimuthal quantum number. Generally, these are rarely used azimuthal quantum number, mostly used in for higher or accelerated state only. Now, if L is equal to 4, it means G orbital. L is equal to 5, it means H orbital. L is equal to 6 means I orbital, and L is equal to 7 means K orbital. Generally, these are rarely, very rarely used, right? These are two questions. You try this by yourself, okay, and show to your teacher. Let me do one for you. The next you do by yourself. So write the possible values of L for third cell of an atom. So for third cell means N is equal to 3, right? And the possible values of L will be 0, 1, 2. 0, 1, 2. It means for third cell there are 3 subcell. That they are A subcell, P subcell, and D subcell, right? So these are in terms of letter, and these in terms of azimuthal quantum number 0, 1, 2. Magnetic quantum number. So magnetic quantum number, it denotes the orientation of the orbital in space relative to the nucleus. So it means, in simple word, so it represents whether the orbital is in x-axis or y-axis or z-axis. Yeah. So in which direction relative to the nucleus the electron is moving. So that particular trajectory is determined or indicated by magnetic quantum number. And the value of M depends upon the value of L. And value of M ranges from minus L to plus L, okay, including 0. So for example, if L is equal to 1, that means L1 means p orbital, right? So L is equal to 1 means p orbital. Then M will be minus 1 and 0 and plus 1. So this, it means px, py, pz, right? So there are 3 types of p orbital, so given by magnetic quantum number. If L is equal to 2, 2 means d orbital, right? So there are 5 types of d orbital, we know that, and that we can also obtain by using the formula or by using the relation minus L to plus L. So -2, -1, 0, +1, +2. So it means 5 types of d orbitals in different direction. Spin quantum number. So spin quantum number, it indicates the direction of so-called spin of an electron in an atom. So I am saying here so-called because the word spin here does not actually represents the rotation like earth, rotation of football or volleyball, etc. Okay. So this word has been used just to correlate or just to address the magnetic property of electron. As you know that when the charge revolves or rotates, magnetic field is produced, right? So just to represent that, the word spin has been used in the case of electron. However, the spin of electron and the spin of earth, okay, they are quite different. So this thing you must know. Now there are only two possible values of spin quantum number. So one is plus half and another is minus half. Plus half for spin up state of electron and minus half for spin down state of electron. Okay, now you evaluate yourself, okay, with this question, how much you have understand or not. So first question, which quantum number is also called orbital angular momentum quantum number? Yes, the right answer is azimuthal quantum number. So it is also called subsidiary quantum number or angular momentum quantum number. Next question, which quantum number denotes the shape of orbital? Which quantum number denotes the shape of orbital? And yes, the right answer is again azimuthal quantum number. Yes, so it denotes the shape of the orbital, whether it is spherical or dumbbell shaped. So that is denoted by azimuthal quantum number. Next question, which quantum number denotes the orientation of the orbital with reference to the nucleus? So the right answer is magnetic quantum number. Magnetic quantum number. So regarding the orientation of the orbital, whether the orbital is in x-axis or y-axis or z-axis, yeah, that is denoted by magnetic quantum number m. So it denotes the trajectory or motion or pathway of the electron, right, around the nucleus. Next question, which quantum number determines the distance of the shell from the nucleus? And the right answer is principal quantum number, right? So principal quantum number, that is small n. So this denotes the or determine the distance of the shell from the nucleus. The value of dash quantum number is independent of other quantum number. So principal, azimuthal, magnetic spin. So the question wants to know that which quantum number is independent of other quantum number, okay, which do not depend upon other quantum number. So the right answer is spin quantum number as well as principal quantum number. So principal quantum number n do not depends upon other quantum number, and spin quantum number s do not depends upon other quantum number. Whereas this azimuthal quantum number depends upon n and magnetic quantum number depends upon L. So what is the right answer? Both 1 and 4. Both 1 and 4. Option number C. Option number C. Which of the following combinations of quantum number is correct for an electron? So for a particular electron, which combination is correct and which are not? So let's see the option. And yes, the right answer is option number B. Option number B, this is correct. This combination is correct. Okay. So here n is equal to 3 and L is equal to 2. So it is less than n. So it is correct. So here it is 0, it is correct. And here it is minus half. Now why others are wrong? Okay, let me explain about that. So when n is equal to 2, L is equal to 1. Up to here it is correct, right? Up to here it is correct. So when n is equal to 2, L can be 0, L can be 1, right? Two possible values are there. So it is correct. Now when L is equal to 1, M can be uh, M can be -1, 0, plus 1, either minus 1 or 0 or plus 1. So here is 2, so it is wrong. So it is wrong. In option number C, n is equal to 4, L is equal to 1. Up to here it is correct, but here again it is minus 2. Yeah, more than this number. So it is also wrong. In last option, n is equal to 3, L is equal to 3. It is equal, so it is also wrong here. So when n is equal to 3, the possible value of L are either 0 or 1 or 2. Yeah, but here is given 3, so it is wrong. So option number B is the right answer. Option number B is the right answer. I hope you understand. Next question, which of the following combinations is correct for an electron present in fourth cell? So in fourth cell means now n is equal to 4, right? N is equal to 4. So option number D is incorrect. N is given here 3, so it is incorrect. Now among these option number A, B and C, the correct option is option number C. Option number C. Option number C. Now why option number A is wrong? Because here n is equal to 4 and L also equal to 4. So it is wrong. Okay, so when n is equal to 4, L can be either 0 or 1 or 2 or 3, but not 4. So option number A is wrong. Why B is wrong? Because here L is 3 and M is 4. So in this part it is wrong. When L is equal to 3, M can be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. But here it is 4 or plus 4, so it is wrong. Okay, so it is wrong. Which of the following combination of quantum number is incorrect for an electron? Now we have to choose incorrect combination. So let's see the option. Option number A, n is equal to 2, L is equal to 1, up to here it is correct. M is equal to 0, up to here it is correct, and this also correct. So option number A is correct. Option number B, L is equal to 2, it is correct. It is also correct. Okay, so option number B is also correct. Option number C, n is equal to 1 and L is equal to 1, so it is wrong here. It is wrong here. Okay, option number C is wrong. Because when n is equal to 1, the possible value of L are only 0. Okay, so possible value of L is only 0. So it is given here 1, yeah, but it should be 0. So this answer is incorrect. This answer is incorrect. This combination is incorrect. While D is right. D is right. Option number D is right. Now next question. The radius of nth shell of a hydrogen atom is given by. So for a hydrogen atom, the radius of nth shell is given by. The right answer is option number C. Option number C, 0.529 into n square angstrom. 0.529 into n square angstrom. Thank you for watching.